Hello friends, welcome to our project. Our project is based on optical character recognition and object tracking. This is the main project directory. Let's get into it. This is the main Python file which we have to run for the project. We are running it through Jupyter Notebook so that we can run it piecewise. So let's run the Jupyter Notebook. It takes some time to load. In that time we can discuss on other details. Our project works basically on a neural network, deep neural network, which finds the character to which the path of the bottle's cap matches. That is, if we move the bottle's cap in a path of an alphabet, say X, then the neural network detects that we have moved the bottle's cap in a path A, and the A will be printed. That's the basic idea of the project. So in this we have to track the bottle's cap, which is done through digital image processing, and after that we'll get the path of the bottle's cap, and then we'll process it using deep neural network to find it that it's an alphabet A. So this is the dataset required for that, which has about 3,72,000 examples of handwritings of different alphabets, and this is the model which we have saved already. In this model we have the deep neural network in it, and this is the media file. The output is empty, we haven't run it till now, and we have some input files. We'll talk about them in a later stage. So let's get to the main project. So this is the main project, and let us run the import statements. While it runs, we can log into Kaggle. So the import statements have been run. So there is different statements for data reading, and various training models are over here. So we'll talk about them in a later stage. So the only thing which we need to know is the model is trained completely, and it is saved in a directory called model, which is present over here. So that is already saved, and then we can get into the main project. So through this code we'll record a video in the directory media input and a number. So we'll record 10 videos which have been already recorded, so we need not run it again and again. So let us, for example, see an example of the video. Clearly see that we are writing the alphabet E with our bottle's cap. So we have to detect that we have written an alphabet E using our project. So we can see another example. So in this we are trying to write an alphabet V using our bottle's cap. So there are 10 examples of this. We will look into it in a more intrinsic manner at a later stage. First, let us get into our main project. So here we are recording the video, and we are flipping it so that it's not a mirror image, and we are writing it into the input, ith input, which is linked to the media input some number, and then when we press the X, it exits, and that's it. That's pretty easy. And then here you'll run another code which basically reads the input from the input directory, and each input one by one in the loop, and then will be output each output, that is the cap binary and tracked. In the tracked will in the cap binary will mask the cap of the bottle, and it will be only the cap will be in the white color, rest everything background will be in the black. So it is done so that we can easily get the background. So let's get it running. So we can see that the media output is blank, and let's start the running, and in the meanwhile we'll explain the code. So this is the first video. So what it does is it divides the video into several frames, and each frame is considered to be an separate image, and from that image we are masking out the cap with the color code. So the color of the cap is similar to green, so we got the HSV format of the color, and then we masked it out, and that is visible in the right side of the frame. And then in the left side what it is done is the cap has got a black border which we have done in the code, and then the path of the cap is highlighted with red color, which also will explain it in the code. So let's fast forward it so that we do not waste time over this video. As you can see that we are writing different alphabets with the bottle's cap. So there's a for loop over here to read each videos separately, and then each output is linked to each one, like output is linked to cap binary and output 1 is linked to tracked. So cap binary, as we have seen, that it is the masked output of the bottle's cap, and output 1 is the left side track, in which we saw that the path of the bottle is getting highlighted, bottle's cap is getting highlighted. And this is the read statement of the video, and this is the center of this is a DQ, and it will be recording the center of the bottle's cap in each of the frames. And this is a kernel used for various purposes such as eroding and dilating, which we'll explain. And this is the lower green and upper green, which is the lower limit and upper limit of the green color, which that means the tolerance of the green color of the bottle's cap. This is used for masking effect. And this remove is done so that the initial 10 frames of the video can be removed. So this has been done so that the luminosity of the camera gets adjusted and tuned in the first 10 frames, and after that it will be stable. So we needed only the stable version, so we have done it in this way. And then we have separated each frame from the video, and each frame will be considered as an image, and each image is given a Gaussian blur and a median blur, so that the noise will get eliminated, and it will be prettier to see and easier for contour management. That means border to separate out the bottle's cap. And then we'll convert it into HSV format, and then we'll mask it out. The cv2.in range will mask the HSV image from the lower green and upper green. So we'll get only the green colored things over here, which is the bottle's cap. And then we will erode and dilate. Erode basically does the soil erosion. It's just like the soil erosion. So the foreground starts to shrink, and dilate is the quite opposite of erode. The foreground will expand. So this has been done so that various holes can be filled, and various things can be disconnected and all. So this has been a principle adopted in the digital image processing for getting a image which is somewhat continuous and all. So that is done to remove basic holes and all. So that's done, and then we'll convert it back into RGB format, and then we'll write it into output, and we can even show it in the screen, which we have done after concatenating it with certain things. So here image is there, so we are concatenating this image with cont. With cont will explain. So it has been concatenated and displayed over the right side. And after this has been, the masking effect has been done, then we'll find the contours basically means the boundary. So after masking, the bottle's cap will be of white color and rest everything will be of black color, so contour management will be pretty easy. So it has been done. And then if there are contours, so if contours means if there is any green color present, which basically means that if bottle's cap is present, so it will take the contour with maximum area. It has been done so that various spots in the background or certain particles in the environment which will be also of the same color, which has to be removed, and only the biggest area that will be of the bottle's cap should be taken. So this step has been done, and after that we will draw the contours which can be visible in the left side frame, in which we saw that black boundary has been given to the bottle's cap. Black is because we are given the RGB as 00 and thickness is also specified, and maximum the contour is given as an argument, and frame.copy is given. Frame is nothing but the frame of the video. So we have created the cont. So in the cont we got the black border for the bottle cap. Okay, and then we will find the center and radius of the bottle's cap. So this is done by using the min and closing circle. So we'll find the minimum and closing circle, its radius and its centers, and then we'll append it to points dot append left. So this has been done so that we'll get to all the path of the bottle's cap. So in each frame the center of the bottle cap is appended to points. Okay, this else is just given for the exceptions. So if the bottle's cap is not present, then 000 will be appended to the contours. That is just for exceptional cases, which normally we don't use it. And then for k in range of 1 to length of points, this is done to traverse through all the points which we have identified as the center of the bottle's cap, i.e. The path through which the bottle's cap has progressed. Okay, so we'll give them a red color with thickness of 40, and it will be done on the cont, and we have given cv2 dot line, so it connects points k-1 with points k. That means it connects the center of the bottle's cap with the center of the bottle's cap in the previous frame. So even though it is cv2 dot line, but we do not see it as line, we see it as curve, because each frame has a difference between each frame is merely how much, 0.36 seconds or something like that. So it will be appearing as a curve only for our visible eyes. And then this is concatenated, and then concatenated into a single frame, and it is shown, which we already seen it. And then this concatenated this cont output is outputted to the output file. Okay, and then the last frame of each output image, in which it has the entire path through which the bottle's cap has progressed, will be saved as a single image for later processing, which we will see. So this is the output file which has been generated. So cap binary 0, which we saw earlier, see, we have seen it as the right frame, so the cap is moving, so that's pretty cool. And its tracked image is also recorded. So you can see that red color for the path through which the bottle's cap has progressed, and there is a black boundary for the bottle, and its image is the last frame of the video of tracked. So we can see that it's very similar to A. So now we will separate this out. Okay, we'll discuss it. Okay, so this has been done, and then we'll run it and we'll show the output and then see. Okay, it's running. Okay, started load. So this was the first image and it is recognized as A. We'll see how it does and all. So second image is E, which is also identified as E. So we'll fast forward. So you can see that all the letters have been identified as correct. Okay, so this was the binary output of the portal's cap progress path. So you can see that 0.6% it was A, and there are other percentages also for various things, but for E it is 0.99 or something like that. So you can see various plots of this. So from these things you can understand many things, how it is and all. So let's check out this example, V example. Okay, so you can see that the maximum probability is for V only, but U also has some probability, W also has some probability, Y also has some probability, which is evident from this chart. So V is similar to U, W and Y, which we can understand from our eyes also. Okay, now let's look into the code. So this is the basic project, and here we are loading the models which we have saved already, and then we'll iterate through I from 0 to 10 so that we can load each letters. That means the last frame of the videos of tracked series, and then we'll load it, and then we'll convert it into HSV, and we'll mask the image of the path. That means the red color thing which was there will be masked out, and that you can see from here, this is the masked out thing. So and then we'll threshold it and we'll make it to binary format, and then we'll resize it to 28/28 because the original frame will be of higher resolution and we need to convert it into 28/28 for the model. And then these values are generated by the model, so we are explicitly mentioning it over here because we are not running the model here, we will run it in Kaggle environment. I'll explain it about it later. So the reshaped image, this has been done for the purpose of the model. So the model takes the input in this format, so we have converted it. Actually it's nothing, it will give the outer boundary for the array, that's it. And then we'll normalize the image. About normalization and all we'll talk in the model. While discussing the model we'll talk about that. PLT-IM show normalized image reshape, this has been done over here. So normalized image is shown and then it is shown, that's it. And then we'll predict, model.predict will predict which alphabet it resembles to the most. So what it does is it checks with each alphabet and finds a probability that the path of the bottle's cap is of that alphabet. So there will be various probabilities which we can see, and it will get the argmax, which takes the maximum value. Okay, so it's all the specifications of the model which we'll discuss later. So it takes the argmax and it is a predicted alphabet, and we'll plot it. So we have plotted it, this is the plot, prediction is plotted, and then it is shown. And this particular code is done so that the right side of the output, right, we saw a block letter A, B and all, no, for that an image is there. I'll show you that. So this image is there, so we'll cut this portion of A when it's predicted to be A, and we'll cut this portion of R when it is predicted to be R. For doing that we have written this code. So we are reading the alphabet and predicted alpha, suppose it is A, it will be 0, so 0 divided by 0 will 5 will be 0, and 0% 0 will be 0, so row and column will be 0. So according to that it will be done over here, and it will be resized to the specified format, and then it will be concatenated with the image and show. So show is the block letters, and image is the last frame of the video, so that is being displayed. So that's it. So our project is completed. So now we will discuss about the model in which we have applied the deep neural networks. So for that we are going to the Kaggle environment. So we are using Kaggle environment because we are getting various features such as GPUs and high RAM and high-end CPUs, etc., which we normally do not get in our personal PCs. So because of these things, the processing of the data will be much faster. Okay, so and we have added the required data set which we already have over here, the A to Z handwriting data set. So that is already added to this over here. So it's already added, and then in the import statement has to be executed. So this is basically import statements, so that's nothing much important. Everything is loaded, and then we'll load the data. So while loading the data, we can see that the RAM usage and the CPU usage might shoot up. So if we are doing it in our PC, then it's sure that it will hang. So it's better to do it in virtual machines. So it's a free environment, so Kaggle is much preferable. Other platforms available are Google's Colab and all, so it's similar to this, but I preferred Kaggle. So it's seen that 8 GB RAM is a must. So my system has only 4 GB RAM, so it's not possible to do it in my system. Okay, so why we are doing this step is because the data present over this CSV file is like initially 100 data will be A, then 100 data will be B. Not saying that it's perfect 100, but similar to that. Large number of data will be A in the beginning and large number of data will be Z in the end. So this is not perfect for the training of a neural network. So we are shuffling the data, okay, and then we are splitting it into train set and test set. So actually it should be an 80-20 rule is there. So 80% of the data should be in the training set and 20% should be in the test set. But we are not following this religiously over here because we have immense data. So we can decrease the test data set. It's not an issue. We have 400 data in the test set. That's quite enough. Okay, so let's just print it. So what does this data represent? So there is about 784 and 1 plus character. So what is a 784? This is nothing but 28 into 28. The image is in black and white. That's the basic sense. And this is the label of the image. That means if it is maybe A, then it is 0. If it is B, it is 1. If it is C, it is 2, and goes on. So it will be of that format. Okay, and then we are separating the label from the training set. So we have successfully done that. So we have separated it and it became 784, and the extra label got into the white training shape. Okay, now we will just display it and all. So this is the first data, that is X train 0, which resembles to D. So Y train of 0 should be 3. A, B, C, D, indexed from 0. So it is 3. So it's quite easy, and we are converting it into two categorical. Two categorical is done so that for the model. So in the model we have 26 classes, that is A to Z, capital A to Z, 26 classes. So what we do here is we'll do a softmax layer at the end. So for the softmax layer to happen, it should be of the format last layer should have 26 neurons. So to have 26 neurons at the last layer, our Y, that means the labels, should be of the format 126 matrix. So we are converting a number to a 126 matrix. That's what's basically happening over here. So there is a raw matrix over here, we are converting it into a 2D matrix. Okay, so which can be seen over here. Initially the y-test was only 3, y-test of 0 was only 3, but after the categorical, y-test of 0 became of this format, that means 126 format, and the fourth element, that means indexed from 0, the third element, the y-test of 3 will be, y-test of zeros 3 will be 1, remaining all will be zeros. So we are encoding it. Okay, so that's being encoded, y-test encoded and y-train encoded to categorical form. So this is done for the purpose of the softmax layer. Okay, and then it's just printed and that's it, and then we'll reshape it. So initially the model was 372 2828 it was 784. Now we will reshape it into 28 bar 28 bar 1. Okay, so this has been done definitely for the purpose of the model, so that we can apply the convolution 2D layers. We'll explain it at a later stage. Okay, that's fine, just run it. So this has been done perfectly fine. And then if you want to see the examples of A in the first 500, so these are the examples of A. It's definitely thresholding as it's a black and white images of A. So if you want to see B or say Z, so the examples of Z will be displayed. So these are the examples of Z. So that's it. And now over here we will take the x mean and x standard. So this has been done for normalization. If you normalize the data, the training of the data will be much easier and the learning efficiency will improve. So we got the mean and standard deviation which we initially used over here. Over here we have used it already, and epsilon, that's also there over here. So these all are specified as far as the model is concerned. So we just normalized the data and it has been done for the training to be efficient. Okay, now we have created a model over here. So we have applied 2 convolution layers over here with ReLU activation. ReLU represents rectified linear unit. So its graph you can see over here. So these all are actually neural network models. So this is the graph. So beyond the 0 means less than 0, it will be converted to 0, and it is greater than 0, y will be equal to x. So this is the basic graph of ReLU activation function, and input shape is mentioned over here. So we have converted all the inputs to this format, as you can see. So it has been done because of the model's specificity. And convolution layers are actually very good for image processing, and an average pooling is done, so a regularization effect will be added to the layers. So what it does is it gets the averages of the layers, of the convolution layers which we got through here, and the matrix kernel used will be 4 by 5. And then we have used another ReLU activation convolution layer, and you can see that the numbers are always increasing, and then we have flattened it so that we can connect it with a dense layer. So a dense layer is a layer in which all the neurons will be connected to all the neurons of the previous layer. So here there will be 16 by 22 by 28 by 28 layers over here, and here it will be again 32 times of that, and goes on, and it will be in a 2-dimensional way. So we have flattened it so that we can connect it into a dense, and then we have added the softmax activation function. So what does the softmax do? The activation function of softmax, what it does is it compares it with the 2 categorical metrics and then decides how much the values should be adjusted. So that's all about the deep neural networks. And we have used an Adam optimizer. There are different optimizers available, such as a stochastic gradient descent, Adam, and many more are there. So Adam is considered to be better than the stochastic gradient descent because there is a momentum constraint over the Adam optimizer. So if you add a momentum constraint, then the learning rate will not get to say deviated, and it will stay intact and it will proceed as required. In the proper explanation, it's like the change in the accuracy will not be abrupt, it will be slowly proceeding, and it will follow a momentous change. It will not suddenly change its direction or something like that. Okay, and there's a categorical cross entropy loss function. So loss functions are defined as such, like how much the predicted value and the original value are differing. So what it does is, if you predict that the alphabet is 50% A and 20% B and 30% C, and the alphabet is originally A, then there is a difference in 50% in the softmax layer of A, and there is a 20% difference in B, and 10% maybe a 30% difference in C. So this is the loss in the calculation. So what we do is, during the back propagation, how large is the loss, that much largely we will change the weights. So weights are the things which we use to build neural networks. So initially weights will be equated to a random number. There are different initialization techniques also. We can even initialize it to 0, but it is not considered advisable to initialize it with 0. We will consider initializing with somewhat nearer to 1, so that it does not explode to a greater extent or decrement to a greater extent. So it, and then these weights have been adjusted to tune. So we are actually adjusting the weights so that the model is perfect. So this is done through our, so we can run it once, and then so it's ran successfully, and then this is a summary of the model. So this is nothing, it talks about the layers. And while training, we have set up 5 epochs and batch size is 512. So the 3,72,000 examples will be divided into batches of 512, and each 512 batch will be trained, and after the softmax layer, loss function is calculated, and through the back propagation layers, through the back propagation processes, we will calculate the changes required in each weights of the neurons, and then we will update the weights as required, as it is Adam, our optimizer. So we will apply a momentum to it, so the weights will not change drastically. So it's better for our training. And after the training, the epoch is 5, so 5 times we'll go through the data. So as the batch size is 512 and the training data is much larger, so even after the first epoch itself, we got a accuracy of 89%, and the loss was 0.36. so over the period we have tried to reduce the loss. Okay, and with the decrease in loss, the accuracy have been increased. Okay, in the earlier case, we have separated a set of data as test data. So why we have separated the test data? Yeah, so the reason is, we have to verify that the model doesn't remembers or by hearts the values. So we did not show maybe a 10% of the data to the model while training, and during the testing phase we will test it with this 10% of the data, and we got a percentage of 99%. Normally while training we get a higher percentage, and there are 2 types of problems which happens while training. There will be bias and variance. If there is a bias, that means the accuracy of the training itself is very low, and if there is a variance, the difference between the training accuracy and testing accuracy is very different. So which basically means that the model is by hearting. Okay, So in this we neither have bias nor have variance, so it's a perfect model. Okay, now the shape of the model, predict. Okay, that's perfectly fine. So it's done, and then we can plot some graphs and see which all have been predicted correct and all. So from here it is pretty clear, z is predicted to be 25 and it is truly 25. So all the green things are correctly predicted. So y is predicted as y itself, so everything is correct. So let us check for some discrepancies. So we can, this is nothing but plotting, and there is nothing much explanation needed in it. So everything is correct. So 99% means you'll find it very difficult to detect which is wrong. So it's very difficult. So we can take a random number like I is equal to 124. So this is the peak and it is very similar to W, so it's like this. So if you try some random number, so this is also a single peak. Sometimes what happens is there will be multiple peaks, so in that cases we'll take the soft max thing. Okay, everything is coming like that, so it's not coming. So remaining thing we have already explained in our Jupyter notebook. So the saved model gets saved over here, over the Kaggle output working model is saved over here, and we have taken this model and put it over here so that we can use it in our Jupyter notebook. So this is all about the project. Thank you and have a nice day.